Greetings, young geometers. So we are now on the first lesson of Module 2. This is entitled Euclid's Geometry. This is a part of this subject because in order to understand modern geometry, we need to understand where it came from. It came about, it was based on actually Euclid's geometry. This was the version of geometry popularized by ancient Greeks, and this gained significant attention with the appearance of the elements. This is a 13-volume book. This is a collection of 13 books written by Euclid, and this was considered as the the most or the main textbook when they studied geometry in the ancient times. I hope that you have read the pages of our textbook that you were asked to read, since I would not be reading these pages in detail, but I would just like to highlight some of the important points in this lesson. So Euclid's definition, the axioms, and the first postulates actually are in appendix A of our book. I have pasted them here. So as you can see here, we have on page 389 of our textbook, you can find there appendix A, where the definitions here, there are actually 23 of them. Then the postulates and common notions, these are the axioms or the basic assumptions as foundation of geometry. Then we have here the first 30 theorems or propositions of book 1 of the elements. Okay, so there are I would just like to highlight 3 of the major observations among early mathematicians of these books, the elements. First observation: even though Euclid realized the necessity of axioms, he apparently did not realize the need for undefined terms. Okay, although it was acknowledged by Euclid that not all statements can be proven, some should be kept as assumptions and consider them as true without any proof. So those are axioms. But he did not mention of the concept of undefined terms. But if we would go back to the first 7 definitions, we can see, we would see that the terms here are basically undefined terms. Like a point is that which has no part. So though there is no clear definition, so we'll just have to read between the lines. We would have to agree on a certain understanding without explicitly explaining what this definition means. A line is a breadthless length. The extremities of a line are points or endpoints, and so on. So up to the definition of the plane. So the concepts therefore of points, lines on a point on a line, then planes, and so on are basically undefined terms. The next definitions are terms defined using the undefined terms mentioned earlier. Observation number 2. In the listing of his axioms, Euclid makes a distinction between those he called postulates and those he called common notions. So what are the differences of these two? Although these are all just axioms. The former, the postulates, were supposedly geometric in nature, whereas the latter were supposedly common to all branches of mathematics. If we would look at this, postulates and common notions here, so we see, these are the 5 postulates of Euclid. First, to draw a straight line from any point to any point, which means 2 points determine a line. Then, to produce a finite straight line continuously in a straight line, meaning a line segment can be extended to make a line. 3, to describe a circle with any center and distance, meaning given any point as the center and a particular distance, a positive number, we can make a unique circle. Number 4, all right angles are equal to one another, meaning all right angles are just congruent. The 5th postulate, if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which are the angles less than 2 right angles. Okay, so these 5 postulates are geometric in nature, whereas these common notions, there are also 5 of them, can be applied to any branch of mathematics. Things which are equal to the same thing are also equal to one another. If equals be added to equals, the wholes are equal. This is the basis for the addition property of equality. Then we have, if equals be subtracted from equals, the remainders are equal. So we'll just have, this time is subtraction. This is just another version of addition property actually. The 4th, things which coincide with one another are equal to one another, meaning anything is equal to itself. The 5th common notion, the whole is greater than the part. Okay, so these common notions can be applied in any branch of mathematics, not just geometry. Okay, the postulates are geometric in nature. So there are 10, all in all, axioms in Euclid's geometry. So that is the second observation. Third, the most important observation. The statement of the 5th postulate is much more involved than the other 4. If you would recall, the 5th postulate, there are a lot of things being mentioned. It mentions of a transversal, that is a straight line on 2 other straight lines. It mentioned of interior angles on the same side of the transversal. It mentions of right angles. It mentions of non-parallel lines. So there are a lot of things involved in the statement of the 5th postulate. So that is what is meant by the 3rd observation. When it was said here that the statement of the 5th postulate is much more involved than the other 4. So this 3rd observation led to a suspicion that the 5th postulate is actually not independent of the first 4, meaning it can be proven. Okay, they thought that the 5th postulate can be proven using the first 4 postulates. So they tried to prove the 5th postulate using the first 4 postulates. But these attempts needed assumptions other than the four postulates. And it was later proven that the assumptions they made were just equivalent actually to the assumption in the fifth postulate. Okay, here is a list of these assumptions which were said to be equivalent to Euclid's fifth postulate. You have here the Playfair's axiom, stating that through a given point, not on a given line, exactly one parallel can be drawn to a given line. This is the Playfair's axiom. This is much more popular in plane geometry. Then the sum of angles in any triangle is equal to 180 or two right angles. This is just also equivalent to the fifth postulate of Euclid. Then there exists a pair of similar triangles. All of these six are actually said to be equivalent to the fifth postulate of Euclid. Okay, so we have here a proof showing that indeed the Playfair's axiom, this one, is just equivalent to the fifth postulate of Euclid. When we say, when we prove such equivalence, that would mean that showing that Playfair's axiom is equivalent to the fifth postulate, that would mean that the assumption of the Playfair's axiom plus the first four postulates would lead to the conclusion, the Euclid's postulate, and vice versa here. Meaning the fifth postulate plus the four other postulates would imply the Playfair's axiom. Let us discuss the first part of the proof of equivalence. This is the proof that the Playfair's axiom, this is the proof of the Playfair's axiom based on Euclid's postulate. Meaning the Playfair's axiom would be the conclusion when we assume the first five postulates. Let a given point P and the line be L. Okay, so you have here a point P so we have there a point P and a line L. Through P, construct a line perpendicular to L at point Q. So that was based on proposition 12. By the way, the first 28 propositions of Euclid were proven using only the first four postulates and are independent of the fifth postulate. Therefore, the truth of the fifth postulate can be based on the truth of the first 28 propositions. Okay, so since it was the proof of such propositions did not depend on the truth of the fifth postulate, so we can use those propositions in this proof. So according to the proposition number 12, we can draw from a line from a point not on the line, a perpendicular can be drawn to the line from a point not on the line. So stated here, let this line be perpendicular to line L at a point Q. Then through P, through this point, construct a second line PR perpendicular to PQ. So this is line PQ. A line perpendicular to PQ can be drawn also at point P. So let's say this another point here is R. This is according to proposition number 11. This time the point is on the line, then a perpendicular can be drawn through the point. Okay, earlier the point was not on the line and a perpendicular was drawn. The lines P, R, and L therefore are parallel according to postulate number 27, stating that if the interior angles of lines cut by a transversal, what was that? That was proposition number 27. Here, if a straight line falling on two straight lines and make the alternate angles equal to one another, the straight lines will be parallel to one another. So, if two lines are cut by a transversal such that alternate angles are congruent, then the lines are parallel, basically. Okay? So, since this angle here is right, this angle here is right, so the two lines must be, this also here is right, so these two lines must be parallel. Okay. Now assume PS is a second line through P. Okay, so suppose there is another line PS through P. Okay, so here is S. Then, by the common notion number 5, the whole is greater than the part. Angle QPS, this angle, must be less than QPR. Okay, so since the whole, this whole angle, QPR, this right angle is the whole and QPS is just a part of it, then this angle must be less than this angle here. Hence, hence angle Q of BQP, where's B? Let us take a look. Okay. So B is a point on line L. So if there is another point B here, B. Hence, angle BQP, this right angle, and angle QPS would now be less than two right angles. The sum would be less than 180 because this is less than 90. Okay, meaning these two angles together would be less than BQP and QPR. Okay, by common notion number 1. But BQP and QPR are right angles, and therefore PS and L are not parallel by postulate number 5. Hence, using postulate number 5, we have shown that there can only be one parallel line. This one. There can only be one line drawn through P which would be parallel to L at a point not on L. Hence, the Playfair's axiom is proven. Next, we have here the proof that if the Playfair's axiom is true, then the fifth postulate must also be true. Okay, the second part of the proof of equivalence. So here we already have a drawing. Let AB and CD be lines. AB here, the solid line, and CD, B lines, be cut by a transversal PQ. So that angle DQP and angle QPB together are less than 2 right angles. So what is meant is this angle here, this angle plus this angle is less than 2 right angles. So we need to show that this would meet, okay, on this side of the transversal. Okay. So that was the proposition number 23, saying that an angle can be drawn so that it satisfies a certain measure. Let PE is parallel to QD PE. So since this is a point outside of line CD, then by Playfair's axiom, you can draw a unique line through P parallel to CD. So that is by Playfair's axiom. Then, since there can only be one parallel line, it would follow that PB is not parallel to CD. That is by Playfair's axiom. Since the Playfair's axiom asserts that there can only be one parallel. Thus, this line AB should intersect CD at a certain point. Suppose that they intersect at a point S on the other side, not on this side. Suppose that the intersection would not be on this side here, but on this side here. So this line will connect that way. So there's a point S there. Then angle SPQ, this together with SQP, this angle here, would be greater than 2 right angles. Why? Because these two are less. Okay, this angle plus this angle would give a sum less than 2 right angles, meaning this sum of these two would be greater than 2 right angles. But then this would contradict proposition number 17, wherein it is stated in proposition number 17 that any two angles of a right triangle cannot be greater than 180. Hence, the intersection cannot be on this side. Indeed, these two should intersect, but the intersection cannot be on this side, but it should be on the side wherein the sum of the interior angles is less than the sum of 2 right angles, or that is 180. Hence, it's proven that the Playfair's axiom together with the first 4 postulates would lead to the 5th postulate. Hence, by this part, second and the earlier proof, we can say that Playfair's axiom is indeed equivalent to Euclid's 5th postulate. Okay, but it should be important. It's important to note that some of the geometric properties, there are some geometric properties that Euclid took for granted in constructing his proofs. Some were assumed without explicitly stating them as postulates or common notions. Here, for example, is the proof, Euclid's proof of his proposition number 1, stating that on a given finite straight line, to construct an equilateral triangle, meaning given any line segment, you can draw an equilateral triangle. So here we have a given line segment AB. Okay, for line segment it is stated here finite straight line. Okay, instead of saying line segment, stated as finite straight line. So given a finite straight line AB, we have to construct an equilateral triangle. But by proposition 3, a unique circle can be drawn using A as the center and the length of segment AB as the radius. So we'll have a circle here. Okay, call it circle BCD. Also, in a similar way, we can draw another unique circle using B as the center and the distance or the length of the line segment, again the radius. So that would be circle ACE. Okay, note that circle BCD and ACE would intersect at a point C. Okay, one of the points of intersection would be C. Consider one of those intersections. There are actually two. Based on this illustration, there are actually two. And consider that as the third vertex of your triangle. Since AC is a radius of the same circle BCD, then it should be equal to AB, meaning this line segment here should be congruent to this line segment here. And also, since BC is a radius of circle ACE, it should be equal also to the same line segment AB, meaning this line segment should be congruent to AB, meaning all three line segments would have the same lengths. Hence, we have drawn an equilateral triangle. Now, where is the flaw in this proof? The flaw is when Euclid assumed that there is a point of intersection between the two circles. Here, it was assumed only that the two circles would intersect. That would only be true if there are no gaps in the points on the circle, meaning this circle is continuous with no gaps. Because if there are gaps, those gaps can be the intersection. There's no point on it. So this can only be true, this can only be assumed if the circle is indeed continuous, which was not explicitly stated as a postulate or as an earlier proposition or an axiom. Okay, so that is the flaw in the proof of the first proposition of Euclid. Again, it was assumed that the circle is continuous with no gaps on it. Next, we have here the proof of Euclid's proposition 16. In any triangle, if one of the sides we produced the exterior angle is greater than either of the interior and opposite angles. We call this now as the remote interior angles, which is mentioned here as interior and opposite angles. So we see here that we have a triangle ABC. ABC, triangle ABC. Then, an exterior angle was formed, angles DCA, by extending line segment BC. Okay, so stated here, let one side of it, BC, be produced to D. So hence, the angle ACD is formed as an exterior angle. So the assertion of the proposition would be angle ACD would be greater than either angle BAC or angle ABC. Okay, so let AC, the proof goes this way. Let line segment AC be bisected at E. Okay, this was based on proposition 10. Okay, so let this be the midpoint of the line segment AC, then this line segment bisect line segment AC. So that proposition states that a line segment has a unique bisector. Let BE be joined and produced in a straight line to F here. Let this be extended so that it ends at F, wherein EF is made equal to BE. So this line segment is made equal to this line segment. That is by proposition 3, that a line segment can be drawn, a long line segment can be drawn so that its length is equal as a shorter line segment. Okay? Let okay, then let FC be joined, that's postulate 1, to 2 points determine a line. But note that then AC be drawn to G, we extend this by proposition 2 that says that a line segment can be extended infinitely to form a line. Now note that this bisects, this line segment BE bisects line segment AC, meaning this line segment here must be congruent to line segment EA should be equal or congruent to line segment EC by definition of a bisector. Okay, let's zoom out here to see the proof. So we have two sides of a triangle congruent to one another, but then proposition 15 asserts that vertical angles are congruent, meaning this angle here this angle should be congruent to this angle. Vertical angles are congruent by proposition 15. Hence, we have by SAS congruence, triangle ABE should be congruent to triangle CFE by SAS congruence, and that is proposition 4 of Euclid. Therefore, angle BAE is equal to angle CEF. BAE. That is that this angle BAE is congruent to angle FCE. Since corresponding parts of congruent triangles are congruent. That is proposition four. But then, the angle ECD is greater than the angle ECF. ECD, this angle ECD is greater than the angle, this blue one, because the whole is greater than the part. Meaning, since this angle is just congruent to angle BAE, then angle ACD, this green one, which is the external angle, is greater than this remote interior angle BAE. So we have proven that the exterior angle is greater than one of the remote interior angles. Okay? Then it could be also proven that this angle is greater than this angle, let's color it red. That this green angle is greater than this by considering this time the bisector of line segment BC. If you consider that, you can show that this would be greater than this one with a similar argument. And since this is equal to this by vertical angles, congruency of vertical angles, then the green angle should be greater than this angle here. Again, since we would do this, wherein this is the midpoint, it can be shown that this angle would be greater than this angle. Hence, this angle is greater than this angle. Meaning the green angle, okay, the exterior angle ACD is greater than either of the two remote interior angles of triangle ABC. Proving the proposition. But take note that here it was assumed that segment BE can be extended up to F, wherein EF is congruent to BE. Although it was indeed stated in postulate 2 that a segment can be extended, but it was not explicitly stated that the line cannot come back to itself. Again, the assumption of Euclid is that if you would extend this, here, there is no way that the point on the line would be the same as B. That was the assumption. But that was not explicitly stated, because it is possible in some other geometries that if you extend a line, it would go back to itself. Okay? In some geometries that we will discuss later. Okay? So it was just assumed here that if you extend BE on the side of E, or on this side of the plane, there is no way that a point would be the same as B, or it would go back to B. Okay? Although, again, by postulate 2, it was stated that it can be extended, meaning it is infinite in extent. Okay? A line is infinite in extent, that is postulate 2. But it doesn't say that it is boundless. Okay, it can be extended, but it can be bounded. Okay, but that boundlessness was not explicitly stated. Okay, next we have the proof of proposition 21. If on one side of a triangle from its extremities or its endpoints, there can be constructed two straight lines meeting within the triangle, meaning the intersection is an interior of the triangle. The straight lines so constructed will be less than the remaining two sides of the triangle, but will contain a greater angle. So, if we would try to draw that, so we have a triangle. Consider this line segment. If from the endpoints of this line segment, two line segments can be drawn that would meet at a point interior to the triangle, then this side plus this side, again this side plus this side, would be less than this side plus this side. That is what is meant by this theorem. But the angle formed will be greater than, let us clear this up. But this angle would be greater than this angle. Okay, so that is what this theorem or proposition asserts. So, the proof. On BC, one of the sides of triangle ABC. Let's make another drawing. So, suppose you have triangle ABC. ABC. A, B, C. On this side, or yes, on this side of the triangle, from its extremities B and C, let two straight lines BD and DC be constructed. So there is these two line segments. This is D. Okay? Meeting at an interior of the triangle. So it is claimed that BD plus DC, BD plus DC will be less than BA plus AC. But angle angle BDC would be greater than angle BAC. Okay. For let BD be drawn through E. So, this can be extended to here and call this point here E. So E. Then since in any triangle two sides are greater than the remaining one, that is actually proposition 20, then in the triangle ABE, in this triangle ABE, two sides AB plus AE is greater than BE. So let us move this up. Again, by proposition 20, it can be stated that, what was that again? AB plus AE these were based on the sides BA and AE of triangle ABE should be greater than BE. Okay. Also, in triangle CED, CE plus ED is greater than CD. CE plus ED. So in this triangle here, we would also have CE plus CE plus DE or ED. Would be greater than CD. So that is again the triangle inequality. But BE plus AC were proved to be greater than BE plus EC. BA plus AC, BA plus AC, this one is greater than so again BA plus AC is greater than BEEC. BEEC. Why is that? That can be shown by adding dB to each side of this inequality. If you add dB here, so CE plus ED plus dB would be greater than CD plus DB. But CE plus ED plus DB is just actually BE plus EC. This one. Because BD plus DE is just BE. So this actually is just this 2 is just BE. So this is basically is just CE plus BE or EB or AC plus EB. CD plus BD is greater than BC. This one is greater than BC. Okay, let us make this clear. So this is B, C. So ED plus DB is just BE, as we see here. ED plus DB is just BE. Therefore, CE plus EB should be greater than CD plus DB. On the other hand, for the inequality AB plus AE is greater than BE, this one here, if we add both sides by EC, so it will become AB plus AE plus EC would be greater than BE plus EC. But notice that AE, this one, plus EC is just AC. So this will just be AC, meaning AC, AE plus EC, sorry. AE plus EC is just AC. So it would mean that AB plus AC would be greater than BE plus EC. Hence, we have this inequality here. But notice that AB plus AC is greater than BE plus EC, and CE plus BE is greater than CD plus DB. Hence, it should follow that AB plus AC should be greater than CD plus DB. Which is what we need to prove right here. So the first part of the proof, the proposition is proven. For the second part, we need to show that this angle BDC is greater than, let's color this one blue, BAC. But take note that angle BDC is an exterior angle of triangle CED. Hence, by the theorem or by the proposition proven earlier, we can say that angle BDC should be greater than angle CED, this one, this remote interior angle with respect to this exterior angle. So it should be greater than angle CED. But then notice also that angle CED is now an exterior angle for triangle ABE. This one. This is an exterior angle wherein this angle BAE is one of its remote interior angle. Therefore, by that same theorem, we can say that angle CED should also be greater than angle EAB or BAE, for that matter, EAB. So we see that angle BDC is greater than angle CED, where angle CED is greater than angle EAB. Therefore, we can say that angle BDC should be greater than angle EAB, which is the second part of the proposition, that the angle formed by those two line segments would be greater than the inclusive angle of the remaining two segments of the triangle, or two sides of the triangle. Hence, the proposition is proven. Now, let us look at the flaws of such proof. In the proof of proposition 21, it was assumed that a line that contains a vertex B of a triangle, that is triangle ABC in our proof, and an interior point, which is D in our proof, must intersect the opposite side of the triangle. Meaning that this line segment can be extended so that the line formed would intersect the opposite side of the triangle, this intersection here, which was not explicitly stated as either an axiom or a common notion. So it was again an assumed concept, such that if a vertex and an interior point will be extended to form a line, then the line should intersect the opposite side. Which was formulated by Pasch in the later time, in the 19th century, which was known as the Pasch's axiom. Okay, so the Pasch's axiom was formulated way later than the proof of the proposition 21 of Euclid. Okay, so in your learning task, you are asked to show that these two statements, alternative statements of the Pasch's axiom, are equivalent. That is, axiom 1 would imply axiom 2. That is true. If axiom 1 is true, then it should follow that axiom 2 is true. And at the same time, if axiom 2 is true, then axiom 1 should follow. Okay, so that is what you are to do in your learning task. Let us move on to the last proof, where again a flaw has been noticed. Here, it is stated that if a straight line falling on two straight lines make alternate angles equal to one another, the straight lines will be parallel to one another. In other words, if two lines are cut by a transversal so that the alternate interior angles are congruent, then the lines must be parallel. Okay, let us now discuss the proof. The straight line EF, here, let this be the transversal. It should fall on the lines AB and CD. Make alternate angles AEF. Let us mark that one. AEF and EFD, this one, equal to one another. So that is the given, the assumption. So it is claimed that line AB is just parallel to line CD. Now if not, so this is proof by contradiction. Suppose they are not parallel, meaning they should intersect somewhere. So when they are produced, they will either meet on this side or on this side. So either in the direction of BD or towards AC. So let's just say they meet on the direction of BD at some point G here. Then in triangle GEF, this triangle here, this triangle GEF, an exterior side would be equal to one of its remote interior angle, which would contradict the preceding proposition, because the preceding proposition states that an exterior angle of a triangle should be greater than any of the remote interior angles. Okay, so that's by the preceding theorem, or proposition 16. Therefore, the lines ABCD when produced will not meet in this direction. So it should be towards A and C. But if that happens, the same argument would follow. If there is a point of intersection here, meaning if they are produced here, they should meet there. So there is a triangle there, this point, let's say P. So you have the triangle EPF, for which this angle EFD is an exterior. exterior angle, which would be equal to one of its remote interior angles, angle PEF. So this exterior and this remote interior would be equal, which would again contradict proposition 16, meaning this intersection here cannot exist, meaning the two lines cannot meet at this side and it will not also meet at this side, therefore the two lines are parallel. So the proposition is proven. But again, the major flaw is that the proof of this depends on proposition 16 there, wherein a major flaw was found earlier. So if this has a flaw, the proposition 16 has a flaw, then so will proposition 27 will be. Okay, so I guess that ends our discussion for lesson 1 of module 2. So it is now your turn to do your task. In activity 2, you are asked to find out flaws in obviously false or faulty proofs. By groups, you are to make your own video discussing the flaws of the proofs given to you in each group, and then also you are required to do your learning task number 4, wherein you are to show that the two statements of Pasha's axiom are equivalent. Okay, that would be all. Thank you for your time and attention. Bye.